Today we are going to discuss on intermediate code generation. What's the need for this intermediate code generation? If a compiler translates the source code to its target machine language without generating an intermediate code, then a full native compiler is required for each new machine. Okay, so whenever we want to create a compiler for a machine, we have to design a new compiler if we do not generate an intermediate code. So it eliminates the need for a new full compiler for every machine by keeping the analysis portion for all the compilers. So till analysis portion will be same. After that, backend only the change will happen. So synthesis part of backend depends on the target machine. Here you can see after the intermediate code comes the backend and target code. So by keeping this much part same, we do not have to design compilers again and again for different target machines. Now, when we design an intermediate code generation process, we should follow the following rules. First is that it should not be very complex. That is, the intermediate code generation process should not be very complex, and it should not be difficult to produce the target program from that intermediate code. Now we have two benefits of intermediate form. One is retargeting is facilitated. That is, we have already discussed. Target machine differs. We don't have to write compiler again and again. Second, machine independent code optimizer can be applied to intermediate representation. Okay, machine independent code optimizer can be applied to this intermediate representation. So this is the position of intermediate code generator after parser and static checker in the front end. So some portion of intermediate code will be used in front end and some portion will be used in back end by the code generator. Now, intermediate languages. Mostly for commonly used intermediate representations are syntax trees, direct acyclic graph, postfix notation, and three-address code. So now we will discuss each of them in detail. First one is syntax tree or abstract syntax tree, usually represented by the short form AST. So it is a graphical intermediate representation and it depicts a hierarchical structure of the source program, and it differs from parse tree. Okay, so it is a condensed form of parse tree useful for representing language constructs. So this is the difference between a parse tree and syntax tree. We have a particular string here 3 into 5 plus 4, and this is a grammar. So we have seen this grammar again. Now for 3 into 5 plus 4, how will we create a parse tree? We'll start from here, right? So 3, we will substitute each and every predictions. So each node will be represent a protection, right? And the leaf represent the literals. Now this is the corresponding syntax tree. See, this is the compressed form of parse tree. Only the operators and operands are present in this syntax tree. So these are the main difference between parse tree and syntax tree. Have a look at it. Now this parse tree is a graphical representation of a replacement process in a derivation. How we derive the particular string, it is shown in the parse tree. Whereas syntax tree is a condensed form of parse tree. Then each interior node represents a grammar rule in parse tree, and each interior node represents an operator in syntax tree. Each leaf node represents a terminal in parse tree, but in the case of syntax tree, each leaf node represents an operand. Then parse tree represents every detail from the real syntax, but syntax tree does not represent every detail. For example, in the parse tree we will include these brackets, right? Parentheses will be included, but in the syntax tree we won't give any parentheses. So this is an example for that. A into b plus c is within symbol bracket by d, but in the syntax tree we didn't give that symbol parenthesis. So b plus c is computed first, then it is multiplied with a, then the result is divided by d. So that is the syntax tree. Now, how we will construct syntax tree for expression. So each node in a syntax tree can be implemented in a record with several fields. So each node will be implemented in a record with several fields. In the node of an operator, one field contains the operator and remaining field contain pointer to nodes of operands. Okay. So whenever there is an operator, there will be operand. So node for operator will contain links to that operands or pointers to that operands. When used for translation, the nodes in the syntax tree may contain additional fields to hold the value of attributes attached to nodes. So we have discussed syntax direct translation, right? So in the case when we are using this syntax tree for translation, we will give fields to hold the value of attributes also. Then these are the functions that we use to create syntax tree. First one is make node. Attributes are operator, left and right. So what will this function do? It create an operator node with label op and two fields containing pointers to left and right, which will be pointers to the corresponding operands. Then second is make leaf id comma entry. So it creates an identifier node with label id and a field containing entry. What is entry? It's a pointer to symbol table entry for identifier. Okay, so it will create a identifier node with a label id and a pointer to symbol table. Then make leaf num comma value. So from this we know that it is a number. So creates a number node with label num and a field containing value, which will be the value of the number. Such functions return a pointer to a newly created node. So these all functions will return pointer to newly created node. So this is an example for syntax tree for the expression a minus 4 plus c. So it is always constructed from bottom up. So first a will be created, then 4, then c, then operations will be performed. So first P1 is make leaf id comma entry of it. So what will it do? It will create a node id with pointer to symbol table, that is to entry for a. Then make leaf num comma 4. Since it is a number, it will create a node with label num and the corresponding value will be stored. Then what we have to do this operation? So it's there is an operator minus, then pointers to the children or operands, two pointers to operands. Then again a make leaf of id with entry to c is made, then plus operation with pointers to the operands. This is the syntax tree for a minus 4 plus c. Now, syntax directed definition to produce syntax trees for assignment statements. Okay, syntax direct definition. The token ID has an attribute place that points to symbol table entry for the identifier. Okay, so token ID will have an attribute place and it points to symbol table entry for identifier. Then symbol table entry can be found from an attribute id dot name comma r. Then, if lexical analyzer holds all lexemes in a single array of characters, then attribute name might be the index of first character of lexeme. Okay, if there is an array of values, then attribute name will point to first character. Now, the two representation of syntax shown in this slide. So, see, these are the two different representation of a syntax tree. Now, what will this do? Minus c. Okay, minus c, then have seen this, right? B into minus c is performed. B into minus c plus b into minus c, then it is assigned to a. That is a one representation. So there is a make node of c, then there is a unary minus with one pointer to the operand. Then another node is created here with b label. Then This is another operator node with points to operand B and operand unary minus C. Then same is repeated on the right side. Then we have to perform addition. So plus and pointer to two operands. Then assignment operation to, that is A is equal to B into minus C plus B into minus C. So this is one representation. Another representation is by using this. Okay. So first B is an ID and it's assigned as 0. Okay, and C is also ID, it is assigned 1. So if I am to perform unary minus of C, I am writing unary minus. Instead of C, I am giving the index value 1. Okay, then I have to perform B into unary minus C. So into is the operator and B is present in index 0 and unary minus C is in the index 2. So I have written like this. So the rest is like that only. So last and finally A is assigned to the value. So assign the value of A. A is in 9 and value is this. Okay, and it is 8. Okay, so these are the two different representations. Next is direct acyclic graph. Okay, so it is a graphical intermediate representation and it also gives a hierarchical structure of a source program, but it is in a more compact way because common sub-expressions are identified. See the previous example, here we will do b into minus c twice and it is assigned to this operator, then it is assigned to a. So when we see this b into minus c is common here, right? So when we represent in direct acyclic graph, b into minus c will be represented only once and two pointers are there, right? So a plus b into minus c. Okay, so b into minus c will be taken twice by this plus operator. So b into minus c plus b into minus c, result is assigned to a. That is the advantage of that. Next is postfix notation. This you have already studied in data structures. So it's a linearized representation of syntax tree. And in postfix notation, we know the operator will comes at the end of the operands. So this is an example, a equal to b into minus c plus b into minus c. So what will we write? ABC unary minus into a PC unary minus into plus assign. So this is the postfix string. Now, these are the postfix rules which you already know. If E is a variable or a constant, then postfix notation for E is E itself. If E is an expression of the form E1 operator E2, then postfix notation for E is E1 dash E2 dash operator. But here dash represent, these are the postfix notations. And if E is an expression of the form E, that is within symbol bracket, then postfix notation for E is same as the postfix notation of for E. There is nothing related to this bracket. So example is postfix of minus E is E minus. Then 9 minus 5 plus 2 is, first we have to compute this, right? So 5 2 plus, then we will compute this. So 9, 5 2 plus minus. And it can be easily find, we can easily find the postfix notation of an infix expression by using a stack. Next is three address code. From the name itself, we can get an idea, or perhaps you might have learned in this computer organization paper itself. So in three address code, the maximum of three operands can be used, right? So three address statement, at most three addresses are used to represent any statement. So each statement contains three addresses at most. So at most means that can be either 0, 1, 2 or 3, but not more than 3. So 2 for the operands and 1 for the result. So it's a general form, we can write it as A equal to B operand C. Okay, operator C. So where A, B, C are operands, that can be names or constants or compiler generated temporaries, and op represents the operator. Okay, so for example, if I want to convert this x plus y into z into a three address form, I can use temporaries. For example, t1 equal to y into c. is the first statement. Then what I have to do, t2 equal to x1 plus t1. This is how we will rewrite it into a three address form. Now, there are certain advantages for three-address code. Unraveling of complicated arithmetic expressions and of nested flow of control statements makes three-address code desirable for target code generation and optimization. We will see this in detail in the coming tutorials. Use of names for intermediate values computed by a program allows three-address code to be easily rearranged, unlike postfix notation. Then it is a linearized representation of a syntax tree or a DAG in which explicit names corresponds to interior nodes of the graph. So these are the three advantages of the three address code. In the coming tutorials, we will be learning these three address code in detail. Okay. Now we will see the three address code corresponding to syntax tree and DAG. So this is a syntax tree, right? Unary minus of C, then B into minus C, then again B into minus C, then adding them and assigning to A. So this is what the three address code is. First we will be giving minus C. So T1 equal to minus C. Then B into T1 will be performed as T2. Then we have to add it. Again T3 is assigned as minus C, then T4 equal to B into T3, this one, B into T3. Then T5 equal to T2 plus T4, this one and this one is added. Then it is assigned to A. Coming to DAG, we are first saying T1 equal to minus C, then T2 equal to B into minus C, then it will be added two times, T5 equal to T2 plus T2, then finally assigning it to A. So hope you have understood this tutorial. Go through it. Watching.